So for the afternoon, we will have invited speakers Hao Su and Andy Zhen, and we will have also paper presentations. And then later, we will have another invited talk from Ruspe Motagi and a panel discussion. So let's get started so that we don't run over time. So it's my pleasure to welcome Hao, who has been a frequent collaborator of mine. I got to know Hao from his time at Stanford, and where I guess Hao has done quite a large variety of things, but Hao is now an assistant professor of computer science engineering at UC San Diego. And he is interested in fundamental problems in various disciplines relating to artificial intelligence. And this includes machine learning, computer vision, computer graphics, and robotics. And more recently, his work has really focused on integrating these different disciplines in order to build and train embodied AI agents that can interact with the physical world. So he has worked on seminal work on ShapeNet, PointNet, lots of nets, which has allowed for the development of this new field, 3D deep learning. And he's basically done quite a bit. And today he will tell us a bit more about his latest work on SAPIEN Plus and the manipulation scale challenge. How?
Thank you very much for the introduction, Manjo. I've pre-recorded the video, so I'll just start to play it.
Hello, everyone. I'm very honored to be here and talk to you. For everyone working in AI, I'm sure that we share the passion of building intelligent agents that can understand and act in the world as we humans do. However, to conduct robotics research, there's a huge amount of engineering work that we machine learning researchers do not care much. This is the big factor that slows down the progress of this field. Today, I'm going to first share some recent work from my lab that aims to reduce this hurdle, which is a high-quality simulation environment, CPM Plus. Then, I will introduce a new robotics challenge built upon CPM Plus, which is friendly to computer vision and machine learning researchers. Before diving into details, let me first point out some of the key differences between the mainstream computer vision research and robotics research. This will help us to see why robotic research involves much harder engineering challenges. We can roughly say that popular vision problems, such as recognition, segmentation, and reconstruction, are intangible AI. There's an agent that is watching the input and make decisions without any ability to intervene with the environment. A typical application scenario is surveillance, which is one of the major revenue sources for computer vision companies. However, when it comes to robotics research, a robot needs not only to watch, but also to execute actions. For example, a robot may move in a room and manipulate certain objects. Typical application scenarios are still on the way. For example, to build self-driving cars in home service robots. So we can summarize the key differences between intangible AI versus embodied AI. First, in intangible AI, dataset constructors collect data and researchers build algorithms to learn from the data. Whereas in embodied AI, other than passively accepting data, agents can actively collect data by themselves and learn to interact with the environment from past experiences. In other words, the efforts we use to put embodying dataset will be replaced by building autonomous agents and interactable environments. Second, in intangible AI, the core tasks are, for example, organization, reconstruction, and segmentation. Whereas in embodied AI, we solve interaction tasks, such as navigation and manipulation. Good representations of the environment from visual input must support the accomplishment of these tasks. In short, to lay down the foundation of embodied AI, we need to find efficient ways to collect interaction data and define a good set of interaction tasks to synergize community efforts. Next, I will introduce some recent work done in my lab. One for building a simulation-based interactable environment, SAPIEN++, and the other for building a manipulation challenge, which is based upon the CPM Plus simulator. To train robots in interactable environments, a natural choice is to use the real world. For example, autonomous driving companies run their cars in streets to collect data. However, this is really costly, considering that we first need to build the hardware. In particular, if the agent needs to explore in the environment, the time cost often becomes prohibitively high, and there might be safety issues when running the iron machines. Another option is to collect data in a simulator. Simulation runs in virtual space, which saves the cost of building hardware and can be very scalable without safety concerns. Last year, my lab released a simulation environment for robot learning named SAPIEN. SAPIEN featured on a rich set of rigid and piecewise rigid objects that are common in daily life. For example, in this figure, the dishwasher the door of the dishwasher can be opened. Since then, the SAPIEN team has made tremendous efforts to improve its quality and lower the bar for researchers to use it. Today, I'd like to show you the new addition, CPM Plus. Compared with the previous edition, CPM Plus has made many changes. But our key mission this time is to save your time when you are doing robotics research. We have provided realistic simulation to save your time of running real robots when prototyping algorithms. We have provided carefully crafted test suites, the low-level modules to save your time in developing algorithms. And we strive to improve the usability of SAPIEN++ to save your learning time and debugging time. Next, let me give you more details. First, I'd like to show that SAPIEN++ provides realistic simulation. While simulators allow you to build embodied AI cheaper and easier, we must mind the gap between simulation data and the real data. An algorithm learned in simulators may not transfer to real. Even if you have read many domain adaptation papers, when the simulation quality is poor, you suffer from the domain gap to make real robots work. Supported by state-of-the-art rendering and physical simulation techniques in movie and the game industry, SAPIEN++ provides your robot agents with highly realistic visual inputs and environment dynamics. SAPIEN++ allows you to select between the extremely fast rasterization-based renderer and the very realistic ray tracing renderer. Here's the performance of the ray tracing renderer on a static scene. The ray tracing is empowered by NVIDIA OptiX SDK, which achieves real-time ray tracing by using a deep learning-based denoiser. Now, this rendering runs on 60 frames per second, Also, note that objects on the table include a bottle of water, which is translucent and refracts lights, metal ball, which is specular, and the whiskey bottle, which is glossy. We have also simulated a RealSense 3D sensor in SAPIEN++. To achieve this, we have replicated an active light-based stereo camera, and here is the active light map rendered by ray tracing. By matching the imaging mechanism of real depth sensors, we can faithfully reproduce the noise and artifacts patterns of real sensors. As we see here, the noise level of translucent and specular surfaces will have a larger depth sensor noise. We have justified that our high-quality visual input simulation can actually lower the domain gap by experiments. Okay, so the task is a 60-pose estimation, which includes both detecting objects and estimating the 60 object poses. We train a SOTA learning-based method, PVN3D, given RGB and a point cloud as input. Note that our model is trained on simulated data generated by SAPIEN++ only, without applying any domain adaptation. It is observed that the model trained on simulated data can transfer to real very well. Both the location of 3D bounding boxes and the orientation of them are accurate. Not only does CPM++ delivers high-quality visual input, we also aspire to deliver a realistic dynamic simulation experience. Now here is a shoulder-by-shoulder comparison of executing the same policy in SAPIEN++ and the real world. We use the X-arm 7-degree freedom arm and a parallel gripper to pick and place the same sets of objects. The same velocity controller-based policy is executed and achieves exactly the same effects. By delivering realistic simulation with low sim-to-real domain gap, we hope to save your time in tuning domain adaptation methods and increase your confidence of developing methods in simulators. Next, I'm going to introduce the pre-built modules in SAPIEN++ to help you jumpstart manipulation-related research more quickly. SAPIEN++ have provided off-the-shelf manipulation environments with carefully chosen tasks and validated 3D objects. We also assume that many vision and machine learning researchers are unfamiliar with motion planning. So we have provided a fast and easy-to-use motion planner with state-of-the-art performance. Let me introduce the environments and the motion planners one by one. We have customized a number of environments to learn manipulation skills, such as opening doors, pulling drawers, pushing cars, lifting kitchen pots, and moving buckets. This environment will be elaborated when I introduce the SAPIEN manipulation scale challenge shown. What makes the SAPIEN++ environment unique is its richness in object variations. You can train your manipulation scale on some objects while test on others. The diversity makes it possible to learn manipulation skills with object-level generalizability. Not only have we prepared the data and the tasks, we also want you to work in a comfortable software system. The SAPIEN used to call ROSE for motion planning. However, while ROSE is the default choice in robotics community, we find that its learning curve is really steep, and researchers will have to manage a complicated robotic system at use time. To help you focus on your learning problem, we provide a motion planning library by integrating state-of-the-art industry packages. Our new motion planner is much easier to install, learn, use, but it delivers even better performance. Our motion planner is Pythonic, that we can build a planner using just a few lines of Python codes. And here is a shoulder-to-shoulder comparison of SAPIEN motion planning library and MoveIt library in ROSE. According to our evaluation, our library runs faster with higher success rate on average. Thirdly, I would like to introduce how CPM Plus may save your time in learning a new system with many new features. First of all, installing SAPIEN is super easy. You can just install the whole SAPIEN system by a single command. After installation, you can follow the tutorials that we have created to play with many demonstration codes. We have prepared examples of building environment and robot models, controlling and planning a robot arm, writing reinforcement learning algorithms, and playing with the renderers. We hope that these well-documented code examples can help you become a robotics expert faster. Okay, that's the introduction into SAPIEN++. We hope to save your time in learning and developing, but achieve more in AI research. Next, I'm going to introduce a SAPIEN-backed challenge to release next month, which targets at learning object manipulation skills. The ability to manipulate objects is profound in AI. Many robotics applications require object manipulation ability, such as assembly, object rearrangement, healthcare, and food preparation. To our computer vision researchers, manipulation tasks also pose many interesting research problems in representation learning. For example, you can play CNN, RNN, transformers to estimate the pose of objects, parse objects into parts, predict the affordance map, or make motion plans. In the context of our challenge, skill refers to action primitives that can be composed to solve complex manipulation activities. For example, if we would move a chair into the room, out of the room, we need a skill to open the door and another skill to push the chair through the door. Now, if we look inside into manipulation skills, a skill can be thought as a translator from a sequence of visual observations to a sequence of arm and hand movement commands. To systematically promote the research of manipulating objects with complex 3D geometry structures, we believe that a challenge on skill learning could be a good starting point, complementing existing working vision on high-level action understanding. Our challenge focused on 5 different kinds of manipulation tasks. And each task targets at a specific manipulation skill. Now, let me first show you the tasks and a demonstration manipulation skill. And then we will discuss the challenge setup details. In each task, we manipulate a single object that belongs to the same semantic category. For example, in the open cabinet task, a robot arm learns to open the doors of cabinets. We have a robot arm installed on a movable platform, and the initial state of the gripper is not far from the object of interest. As a skill learning task, there are no preconditions to be satisfied. The robot will just take the visual observation of the object as input and needs to change the state of the object in front of it to a desired goal state. Here, the robot opens the door to be larger and the pre-specified angle. And we will use success rate to measure the performance. In the open drawer task, a robot learns to pull out the drawer of a cabinet. Note that we have set realistic force and friction coefficients to objects and the robot under simulation. And we do not restrict the way to open the drawers. You can either open it by pulling the handle or by pressing the side and drag, as long as it is feasible and it finishes at our desired goal state. In the open kitchen pot task, a robot arm learns to hold the handle and lift the lid to a certain height. In a push chair task, 2 robot arms need to collaborate and push the chair to our target position. In a move bucket task, 2 robot arms collaborate to lift a bucket that includes a movable sphere and put this bucket on the patio. We have prepared 2 challenge tracks, and you can pick the track that fits your research background and interest. Our first track is an offline learning track. You may think that this is a learning from video demonstrations challenge. Like other vision and machine learning challenges, we split objects to manipulate into training, validation, and test sets so that they don't overlap. In this way, we can test the object level generalizability of manipulation tasks, manipulation skills. For this track, since the learning must be offline, the agent is not allowed to interact with the environment at training time. Instead, for each object to manipulate, we will present a number of successful demonstration trajectories. And you can use your favorable algorithm to learn a skill by referring to the demonstrations. For example, you may use a transformer to imitate the demonstration trajectories we provided. And we will explain details of the demonstrations later. Now you have access to a number of validation environments which are allowed to be interacted. And therefore, you can evaluate the performance of the offline learned policy. So why do we include this offline learning track? We feel that this track is fairly easy to start with, because you can simply use supervised learning to imitate the demonstration trajectories. Besides, it is not as resource intensive as the online learning track, which will be introduced soon. You may use a single GPU to kick off the robotics research. And we hope that this setup would allow you to focus more on network designs and optimization techniques. Besides the offline learning track, we have also provided an online learning track. In this track, at training time, you can not only refer to the demonstration trajectories we have provided, but also interact with the environment in any way you want to improve your policy. Now, in this setup, you can try your favorable reinforcement learning or other online learning algorithms. Next, let me show you what a demonstration trajectory is. Simply speaking, a demonstration trajectory includes a sequence of transitions. For example, at time t, the environment is at state st, and we will provide you what the robot observes at time t in terms of the image and the point cloud. We will also provide you the demo action to take at this state in the form of robot joint angle change. And our demo also includes the observation at the next time moment t+1 and the reward the agent receives at the state. If you are using imitation learning to solve this problem, you can just train a network that takes the ST as input and predicts the AT. Okay, we have finished introducing the form of challenge. Hope that you will have interest to participate. One question that you may have is how we collect the demonstrations. The most existing benchmarks for action learning collect demonstrations through crowdsourcing. While this is definitely an important way to solve our manipulation skills, it is still quite hard. This is quite hard. Not only high cost will incur, the more challenging issue is that controlling robot arms and the grippers is not easy because they have a high degree of freedom. Is it possible to collect demonstrations automatically without human annotation efforts? Ideally, we would like to train an RL policy on all the environments together, but we find it also to be quite difficult. Now, to solve our open cabinet task by reinforcement learning, we tried to train SAC with 1 million samples in SAPIEN. SAC is a reinforcement learning algorithm. We can see that we achieved 100% success rate to open a single cabinet. However, when we try to jointly train on more cabinets, the success rate quickly drops to 0%. Therefore, instead of training a single reinforcement learning policy for all environments, we take the divide and conquer approach and solve each task independently. In this way, we have obtained the policy for each environment. Okay, thank you very much for listening. And this is the introduction to the new edition of SAPIEN and the Object Manipulation Skill Challenge. Now, both of them will be released early next month. Stay tuned at the news at the Twitter of my lab. Yeah, thank you.
Thank you, Hao, for the nice introduction to SAPIEN++ and the Many Skill Challenge. I hope this inspires many members of the audience to participate in the challenge and also use SAPIEN++. So we have time for some questions. So please feel free to raise your hand for questioning or to just type your question in the chat directly. So let me start off by maybe asking Hao a couple questions. One thing that I really like about your work is that, for instance, the SAPIEN work is trying to make it easy for vision researchers, and also I think even make it easier for robotics researchers to do work at this intersection of perception and interaction manipulation. And I was wondering, even with the existence of these, so we're seeing this workshop, there is this development of a lot of different simulators. And I was wondering, do you have some opinions of what students who want to work at this intersection, what should they know, even if they have access to such nice simulators? What do they still need to know that they
Yeah, that's a great question, really a great question. That reminds me of my experience of learning deep learning back to like, I guess the 2000, maybe 9. Yeah, so at the time I heard about deep learning, but I also feel that it's kind of a, well, mysterious and not easy to learn. Until I start to see like the PyTorch libraries, right? And like the Caffe and TensorFlow. So you play with the basic things, right? And you get a sense of it. And then you realize that, okay, the learning gets easier. So that's one of the motivation for this universal CPM Plus to actually provide a rich set of tutorials. Yeah, so we have provided examples and tutorials actually covering, give you experience of a modeling environment, which I think actually, if you're using a simulator, this is important. You need to get certain sense of modeling, what the simulator could do for you and what is still not good enough. And also we provide certain codes and tutorials for you to like quickly get a sense of how to do planning and control and reinforcement. Yeah, so that's my opinion. So somehow, not only for like mastering the machine learning techniques, but also understanding certain kind of like how the environment's modeled, the classical robotics without learning, these are still useful. But the best way to start it is actually to play with some codes, yeah, without much spending much time.
Thank you, Hao. So we has a question. How accurate is the contact modeling between the gripper and the objects in your simulator?
That's another great question. Here's my basic answer. First of all, as I have played in a video here, you'll see that it's possible to give you like a pretty reasonable grasping effects, okay, in the simulators. And if I summarize more precisely, it relates to whether you are grasping like a rigid objects or deformable object. And when you are doing the grasping, whether the contact points are stable or they will constantly change. And one of the challenge for grasping deformable objects is that the contact points will actually change. You think that the area for the contact surface is changing, right? So if your contact point is not frequently changing, like if you are grasping with stable relations between a gripper and the object, or somehow is slowly changing, my personal sense is that the current simulators are already well able to simulate well. Okay. But if you're, for example, playing with like liquids or like deformable objects, or there's a very frequent change of contact points, then there's still a big space to improve the simulations. Okay.
Are there other questions for Hao?
This is the one.
Yeah. Maybe I just ask another question about the tasks that you have in your challenge. Can you say a few words about how, I know there's a lot of work in like say grasping, in pick and place and those things. Can you say a little bit about how why should somebody be excited about doing the tasks that you are proposing?
Yeah, thank you. First of all, we actually have carefully selected tasks based on two criteria. First is they are important and basic skills and with value of research, which means that they are not this kind of well-solved problems. And secondly, they are the tasks that simulators could really support well, which corresponds to Yu's question just now. Actually, there are something very interesting. Like for the opening of the drawer, as this video plays, there are many possible ways to open it. Okay, if you're using like a logic-based planner, maybe you will say, grasp the handle. But in fact, it's also possible to explore many interesting ways to open it. And for many reason researchers, you might be like used to solving predefined tasks, whereas the exploration experience of robots is quite interesting, and you could get a sense by playing with our challenge. And second is, we actually have included certain kinds of complex manipulation skills that requires the collaboration of two arms and is really hard to be solved in a traditional robotic way, we think. Like here, the chair is the under-activity system, which means that there's a higher degree of freedom than the control signal that you could get. And so how do you solve this kind of a very hard control problem, but also involve the collaboration of arms? This is also quite interesting. So these are just some of the dimensions I'm pointing out. There are other kinds of interesting parts that I think that you will sense it when you start to play with it.